Hello everyone. Today I will discuss about one possible explanation of the LSND and MiniBooNE access. This is a brief outline of my talk. I will discuss about the LSND and MiniBooNE access events, a possible solution to the access events, and the connection of our model with the anomalous muon G-2 and CDF II W-mass measurement. Then I will draw the conclusion. LSND and MiniBooNE were two short baseline neutrino experiments. This is the schematic diagram of the MiniBooNE experiments. This 8 GB protons hit the beryllium target and it produced a charged ion. We can use the magnetic horn to allow either the positively or negatively charged particle in the decay pipe. This charged particle decays to corresponding charged leptons and it produces the neutrino. This neutrino travels 450 meters before reaching the detector. For LSND experiments, the energy of the proton is much smaller, 800 MeV, and the baseline is 30 meters. This scintillated type of detector can't distinguish the signals from electron, positron, gamma, and under certain conditions, the E plus E minus pair also. In the upper panel, we show the flux of the LSND MiniBooNE experiments. This flux peaks around the 800 MeV, and we can see that this flux falls rapidly after 1.5 GeV. For LSND, there are two types of flux. One is dark flux, and another one is deep flux. Dark flux where pion decay at rest. So we can see that there's a line spectrum for mu beams, and there this mu plus decays, and that produce the mu bar beam. And whereas deep flux, pi plus decays when it's in motion. So we can see that the mu energy is here higher compared to this mu or mu bar beam, but the amount of flux is 50 times smaller than the dark flux. MiniBooNE is looking for electron-like signal in the final state. So their main beam is the mu beam. They are looking for the electron in the final states. For LSND, they are looking for the inverse beta decay signals. The main beam is mu bar beam. They are looking for the positron and the neutron. So this neutron is captured by the free hydrogen and it produces the 2.2 MeV gamma in the detector. In the upper panel, we show the LSND MiniBooNE data, and in the lower panel, we show the LSND data. So this is the total background for the MiniBooNE experiments, and these are the observed data. We can see there is an excess events up to 450 or 500 MeV, whereas the flux peaks around 800 MeV, and there is no excess in this region. This is the angular distribution of the events. We can see that the 1/3 events in the first beams, and also there are excess events in the non-forwarded beam also. For LSND, these are the backgrounds, and these are the observed data. So we can see that there's an excess of events, and in the angular distribution, we can see that there is almost flat distribution of the events. The combined significance of these two experiments is 6.1 sigma. Here we consider one general constraint. MiniBooNE also ran in the beam dump mode, so they removed this beryllium target, and the proton beam hits this 4 meter thick steel. So if the excess is coming from dark matter, so in this setup, they also expect that there is an excess events in the detector. So here for the thin target, this pi plus pi minus will be decaying in the decay pipe, and it produces the neutrino. And whereas this pi zero produce the dark matter particles, which also reach the detector. But for the thick target, this pi plus pi minus absorb, and this will not be directed towards the detector, and the neutrino flux will be reduced 30 to 50 times. But this dark matter reach the detector and can give the signals. So if we scale the POT, then we'd expect that 35 excess event in this setup. However, they observe only 6 events, while the background was 9. We can conclude that the excess disappears when neutrino flux is suppressed. So the excess in the MiniBooNE is related to neutrinos. So there are two possibilities for this excess. One is unknown backgrounds, and another one the new physics. We'll focus on the new physics part here. So new physics could appear at the production while this K plus pi plus decay. So there could be a heavy sterile neutrino that could be produced here and decays back to the electron type of neutrinos. In the propagation, like mu to nu oscillation driven by EV scale sterile neutrino, and there is another possibility that detection where heavy sterile neutrino produced and it decays and giving the visible signal in this detector. We'll discuss this part. So here the constraint on the sterile parameter space. These are the region allowed by the LSND experiments, and we can see also here the LSND and MiniBooNE preferred parameter space. And these almost all the regions are ruled out by the disappearance experiments like Minos, Diowe, Bouguet 3. Also, the MicroBooNE is an ongoing experiment. So MicroBooNE recently measured the electron type of signals, and they find no excess in the electron type of signals in the detector. So they constrain the sterile hypothesis also. And they also measured the delta goes to N gamma process, and they conclude that this can't explain the MiniBooNE excess. Here we propose two Higgs doublet models with the dark singlets scalar 5 prime. Also, we have 3 right-handed neutrino that generates the neutrino mass, and that also take part in the interaction in the detector and give the signals both in LSND and MiniBooNE experiments. This is the potential for the two HTM one singlet scalar. We give wave only one of the doublet, and this doublet remain waveless, and this H prime also waveless. This is the Yukawa interaction terms. So here is the Feynman diagram for the process. Nu comes and it produces N2 in the final state, and N2 decays to N1 and H prime, and this H prime decays promptly to E plus E minus pair. So the masses and the other parameters given in this table. So this process could be mediated by both capital H and H prime. The mass of the H prime is 17 MeV and capital H is 750 MeV. And this mixing angle is 0.1. So the coupling of H prime with the U and D quark or within this vortex is suppressed by this mixing angle. So this is the cross section for the process. Both the incoherent and coherent part will contribute. And mainly the coherent contribution is coming from the light scalar 17 MeV, and that gives like 15%, 17% contributions. So we can explain both LSND and MiniBooNE excess in our models, and we can see that we can accommodate them both the energy and angular distribution in our models. So for LSND, the process will come from mainly the deep flux. So for mu is coming and it knock out one of the neutron in the final state, and it produce N2. This N2 decays to N1 and H prime, and H prime decays to E plus E minus pair. And this neutron is captured by the free hydrogen and produce 1 gamma. So the signal looks like inverse beta decay. We use 8 MeV as the minimum energy transfer to the neutron to knock out from the material. For carbon, a similar experiment like LSND, they didn't see any excess. So, but for the carbon, the deep flux is very small. So we'd expect no signal in the carbon in our model. both capital H and H prime contributes, and the H prime contribution is small because of this sign delta. But since it contributes more coherent in the coherent contribution, it will help to populate the forward bins and the angular distributions. The masses of N2 and N1 are important to obtain the correct number and distribution of the excess events. Here in this paper, we discuss like why some model of Z prime can't explain the LSND excess events. So here we for like 1 GeV mass of the Z prime and Higgs. So we can see that for the Z prime things, the cross section drops very rapidly when you go from the MiniBooNE to LSND energy range. But for H, the drop in the cross section is not that much. So this will help in our case to explain the LSND excess. Another thing is that for the Z prime, the cross section remains almost constant when we increase in energy. So that helps actually. But for capital H, the cross section drops. So this helps to explain to evade bounds from the CHARM2 and MinAlpha experiments. Now I'll briefly discuss about the muon G-2 and the CDF II W-mass measurements. So we know that anomalous magnetic moment of muon differs from the experimental data and theoretical prediction in the standard model. This delta mu now the discrepancy is like 5.1 sigma, and delta mu is 2.74 into 10 to the power minus 9. So in our model, we have both H prime and capital H. So we can explain this anomalous magnetic moment, and our benchmark values satisfy this anomalous magnetic moment data. The recent measurement of the CDF II W-mass is this one, and the standard model prediction is like this. So these two data differ by 7 sigma. Also there is a tension between the world average and CDF II measurements. But we'll here consider only the CDF II W-mass measurements. In our models, we have both capital H and H prime. So we fix these things for the LSND and MiniBooNE experiment, but we have charged H plus minus and pseudo scalar. That is still a free parameter. And we use these things to explain the W boson mass. We can calculate the W boson mass using this formula. At the tree level, this delta is 0, and we'll get this MW. But when you consider the higher order correction, this delta are not equal to 0, and this delta fraction coming from the QED corrections, row parameter correction, and this term is coming. This is the remainder part coming from the box diagram, vertex diagram. So delta SM is like 0.038. When we put these values, we'll get MW mass to be 80.3564. But here we use the H plus minus to vary this row parameter. So we can calculate in our models the row parameters. And we can see that if we vary the mass of MA and MH prime, we can actually accommodate the CDF II W-mass measurements. I will draw my conclusion here. So evidence of anomalous signal short baseline neutrino experiment increased over the time, and our model can explain both LSND and MB excess, and we can also accommodate the muon G minus and CDF II W-mass values. MicroBooNE is an ongoing experiment. It will look for the plus and minus period in the near future. So this will provide a test of our models. Thank you all for your kind attention.